So first, good morning, everyone, and welcome to our computational social science webinar. We are very happy to have our colleague, Professor Huang Liqiang from the Department of Psychology at the CUHK. So let me first briefly introduce Professor Huang. He's an associate professor in the Department of Psychology and earned his PhD in experiment psychology from UC San Diego. And Professor Huang's research focuses on analyzing various aspects of human communication with a particular emphasis on visual attention and perception using very, very large scale online experiments and machine learning and conceptual models, which also today's talk I guess that you will see that how they combine all these kind of tools together. And another thing, at least for me, unlike most of us in computational social science, just the board of the methods developed from computer scientists. Professor Huang's work actually not just use this methods, but also later you will see that it has fundamental implications for the design of many computer systems. So we are very privileged to have him here today to share his insights with us. So without further ado, so please join me in welcoming Professor Huang.
I'm very happy to be able to talk here today. First, I want to make a note or clarification. So, because my area of study is like the basic science side of experimental psychology. So, and I gave this talk earlier to an audience of mainly psychology students. So perhaps like because I know the audience today are very good at computational modeling and everything. So maybe to you, I will be like a student learning and please give me some comments because I just learned this in recent years. So I will get started. This talk is mainly like a personal sharing of why I switched gradually over the years from doing traditional psychology experiments to these large-scale experiments. Why is it necessary? So I will start with my earlier studies on the theory-driven studies. Okay, my initial perspective. So that's the kind of like what happened when I was a graduate student and postdoc and assistant professor in those years. My initial perspective on experimental psychology was that it was still in its earlier stages, and that once it reached full maturity, it would resemble physics to a great extent. So what do I mean exactly by being like physics? So basically, we will have a theory that's simple, precise, and broad. And as we all know, in social science, we are not quite there yet. But at that time, I think we will be there, and as long as we work hard. So with that idea in mind, I dedicated the majority of my earlier years to developing a Boolean map theory of visual attention, and those were the representative publications from that line of study. And so it's not the main topic today, but I do want to tell you briefly what is a Boolean map, so you have some idea of just what kind of like a theory-driven studies I was doing. So essentially, a Boolean map is a data format in which one feature is associated with multiple locations. Feature in this particular context could mean color, orientation, etc. But I will give you example on color. And we propose that it underlines the content of information that can be seen at a given moment. So basically, at any instant, you see a Boolean map. That's what we argue. So what's the evidence? What's the finding? So for example, here, I ask all of you to try this. It should be easy for all of you to know that, to confirm that the disks occupy the same set of locations on the left side and the right side, right? Quite easy. But to know that they contain the same set of colors, like you have red here on left side, red here on right side, green here, left side, green here, right side. Although they are different locations, the set of colors in here is the same as the set of colors in here exactly, just like the colors, just like the locations. But it's much more difficult to know that. To know that, you have to check the colors one by one. Some of you may say that's just because the color is a much weaker information than the location, but that's not the case. If I give you one color versus one location, you're roughly equally good on this. So it's really, you have a problem with multiple colors, but you don't really have much problem with multiple locations. So this is the kind of evidence we use to argue for the Boolean map theory. And with this and many other lines of evidence, we propose this Boolean map theory. And at that time, I harbored a high level of optimism and believed that with persistent efforts towards constructing better theories and designing refined experiments, creating a theory similar to that of physics would not be an impossible task. So that's what I believed back then. However, I eventually reached a point where I could no longer proceed. You probably don't hear this very often in a talk, but I do want to tell you this, so you understand why I think this approach is fundamentally limited, and we need to switch to large-scale experiments. So basically, after doing this for several years, I have to stop. So the main difficulty lie in two areas. Firstly, like all concept-based theories in psychology, this Boolean map theory was unavoidably weak. By the time Boolean map theory was published in 2007, I was already fully aware of the problem of theoretical weakness. I mean, that's nothing mysterious. Everyone around me, including my mentors and colleagues, have been telling me that. So that's the main thing I was working on in those years. I was working hard to address it, to make it less weak, to make it precise. So in 2008, I told a friend that I intended to spend the next 5 years conducting a series of studies aimed at concretizing and quantifying the concepts involved in the theory. Indeed, that's the first GRF grant I get. So on this. So my goal was to produce a clear set of evidence that would either support the theory or form the basis for a new one. And then I estimated a 30% chance of the theory being supported. But more importantly, regardless of the outcome, I believed that a unified theory capable of answering all questions would emerge. So basically, I hope my theory would work. But I was pretty sure back then that even if my theory does not work, as long as I have this clear set of experiments, clear set of findings, I will come up with some unified theory that can answer all the questions. Then my friend smiled and replied, what if there isn't a consistent theory that emerged from this evidence? And to this, I replied, I consider that outcome to be unlikely. Truth is always grounded in a set of principles. And with a precise method of examination, these principles can be reviewed. So that, in theory, will always work. But I was naive to thought it can be readily accomplished. So when I look back, I realized how naive I was back then to hold such a belief. By 2012, most of the planned experiments had been completed. That's 5 years after the theory was published. And their results were already clear, evident. once the variables were precisely quantified, it became clear that no theory could completely account for the wide-ranging results. Neither my theory nor any of the existing ones seemed to work, and I couldn't come up with any new theories that would be effective. So that's a huge disappointment for me, as you can imagine. And I spent years, like in a days, thinking about it. So, like most of my colleagues kind of like realized I become like more silent and less. I just publish less papers and I don't talk that much thinking about it. But after a few years, I come to the realization that my pursuit of a simple theory, so I was trying to figure out what exactly was wrong with my approach. And I realized that my pursuit of a simple theory may have been misguided from the start. So the human mind is very complex, and even a relatively narrow and straightforward aspect of it, like attention, requires a set of intricate principles to be adequately described. So that's like the result of my thinking. So to make it a little, to explain it a little with a little more detail. So this is not what I think. So hence, when a theory tries to elucidate complex mechanisms, it encounters an impossible trinity concerning three criteria: simplicity, precision, and breadth. So a theory can achieve any two of the three criteria, but it cannot fulfill all three simultaneously. So specifically, those thin line here, they refer to the specific findings that are very precise and very simple, but they are very narrow also. Like they're just those particular findings limited to that particular task, particular stimuli, particular paradigm, exactly the way how to do it. And on the other hand, we have those general principles, general notions. In psychology, we have, for example, working memory, which is what I'm working on. And that's a very broad concept, can be used on many situations, in many situations, but it's vague, and the way of using it is always a bit different in every cases. So those are the general but vague principles, which are those which is yellow line. So both of those, you can easily find them in the literature. But this is what I want to do, and you don't really see that very often in the literature, is that a study that's both precise and broad. But then, because it's impossible to get all three of them at the same time, then you have to give up simplicity. It means that you have to be complex. So that's the purple line, basically trying to review the complex principles. That's the result of my thinking. So that's how I have been trying to do in the later years, those purple line. So after making that decision, I moved to I tried to figure out, okay, what exactly should I do? Then when working towards developing a complex theory, the main challenge was a gap between the limited amount of information from experiments and the vast amount of information required to elucidate the complex principles. It's by the knowledge of money, it's like you need a lot of money, but you only have very little. Then how to solve that problem? On the one hand, you try to make more money. On the other hand, you try to reduce you try to cut some of the spending, and it's the same story here. Like because we need a lot of data and we only have very little. So first, we try to collect more data. And on the other hand, we try to narrow down the scope a little bit so that we don't require that much data. So all in all, I like my plan back then, like after 2012, was to undertake what I call a systematic exploration of a medium-sized field. This involved identifying a research area of medium size, standardizing the existing studies into a unified experimental method, and then repeating the experiments to summarize the rules. So I initially planned around 10 such projects, some of which were abandoned after a brief attempt for all kinds of reasons. Ultimately, I was able to complete 3 of those 10, but only 1 was clear enough to be publishable, so which were subsequently published as the FVS framework. So what is FVS framework? So basically, researchers utilize various types of stimuli and tasks in the field of attention and perception. However, the relationships between these different stimuli types and the tasks remain poorly understood. The FVS framework aims to shed light on both of these aspects through a sample of 1,700 participants, which is considered large within the standards of experimental psychology, because normally we only have something, sometimes 20, sometimes 50, and 100 is already considered to be fairly large. 1,700 is very large in that standard. And this is a paper that with this FVS framework. So exactly, these are the 16 stimulus types I try to address, like color, shape, size, spatial frequency, etc., which I try to cover all the representative stimuli types in this area, and also all the 26 different tasks in this area. Then this is what I argue is the relationship between the 16 stimulus types. So in a word, I come up with a 3-dimensional space, which I think perfectly explain all the stimulus types and the tasks. So I name those as F, V, and S, 3 dimensions. And so this is the relation between those stimulus types. This is the relation between those 26 tasks. Again, this is not the main topic today, so I wouldn't get into the details, but I just want to give you some sense about what I tried in those years. Okay, and then I moved towards the large-scale experiments. So despite the progress made in the case of the FVS framework, I found that the systematic exploration of a medium-sized field, so which was what I did between 2012 and 2019, something like that. And it was not as effective. So all these years' effort, just this one big paper, but all the other projects then is not clear enough. So it's not as effective overall as I had hoped. Although there were all kinds of reasons, several issues, I believe the underlying reason for all of them was just one, which is the inadequacy of data. So in other words, while I have made some progress in narrowing the gap between available and required information, I must do it much more dramatically to really close the gap. So in a word, we need more data, a lot of high quality data, specifically designed for research purposes. So that's like how I got to large-scale experiments. So of course, large-scale experiments is not just it's not self-evident how you should do it, and there's many possible ways. And I thought about how to do it, and several other factors contributed to my decision to shift towards large-scale experiments, to this particular way of doing it. So one of these was stumbling upon an interesting paper that argued for a more solution-oriented approach in social science. You may also recognize this because our dean sent this to us a couple of times over the years in relation to preparing for GRF grant. And this is how I got to see this. And it was, I was lucky that I saw this. So this helped me in making up the plan of doing it. So specifically, I thought that it would be a good idea to obtain a comprehensive data set covering all aspects of a research question, but without like a particular hypothesis or anything, and then search for a solution. Solution here means the best model for this data set. Before telling you about this particular logic experiment I did, I also want to share a little bit about just overall feeling. So in a large-scale experiment, we study a topic using data sets that are hundreds of times larger than usual. However, what is most significant is how the experience of conducting research has changed. During my 20 years of running conventional psychology experiments, I always felt like a detective holding a glass of water, searching for clues. Even though it was sometimes easier, I still needed to deliberately look for clues and interpretations. It's always kind of like you have to do it intentionally. But with large-scale experiments, the experience is entirely different. When I began data analysis, a massive amount of information just surrounded me, rushed me, leaving me breathless. So you never worry about not having enough information. Now you have too much information. The challenge is how to like make use of it, how to interpret it. Like before, we always live in the environment of not having enough information for us to interpret. Okay, so finally, we're getting to this particular study, which I call the first piece of the puzzle. Obviously, it's not, we will not end here, but that's the only thing I have finished. I have finished data collection of 4 projects, but it's the only thing I have published so far. So this is recently published in Nature Human Behavior, and the title is Quasi-comprehensive exploration of the mechanisms of spatial working memory. So you may wonder why spatial working memory? That's not because it's particularly important or particularly suitable for large-scale experiments. It's simply because my familiarity with it, because I have been studying it for the purpose of Boolean map theory. But in any case, that can serve as an example of how to do large-scale experiments in like our area. So the general approach is this. So in the typical theory-driven approach, one proposes a mechanism or theory and test its predictions. But if you want to explore all mechanisms, this is apparently inadequate because there are too many possible mechanisms. As an alternative strategy, the present study adopts a data-driven comprehensive exploration approach. I conduct a large-scale experiment to systematically measure the spatial working memory across many patterns, and then look for the simplest model that explains the data. If the data can be largely explained, then we can see in an empirical sense that the underlying mechanisms have been largely discovered. So this is this particular research question. So how do we remember a spatial pattern? And we have many of them, and those are some sample. By looking at this, I'm sure you realize that some of those are easier than the others. Why are they easier? One may point out that the more regular ones can be remembered more easily, but again, the regularity is not a self-evident mechanism. Then, so if you believe it's regularity, then you can see the research question is, what is regularity in relation to memory in this particular case? So in any case, let's just re-ask the question another way. So this is a task, particular task. I present 6x6 array of items, and then the observers, the players, have to remember 8 of them, and then after 1 second, they have to report those 8 by tapping on those 8 cells according to their memory. Of course, they're not always precise, and sometimes they make mistake, and then we give them feedback on that. So this experiment included a total of 80,000 patterns, and I measured a total of 35 million responses on those patterns. So those are the results, of course, just on some sample patterns, and this 10 sample patterns from the easiest ones to the most difficult ones. And how to see this? So for all those cells with items, I use green to plot those with, you have very precise answers. You report it always very precisely. And the red ones are those you always report, you report not very precisely. You make a lot of mistakes. You miss them a lot, the red ones. And for all those empty cells, you still respond to them occasionally. And those are what we call false positive. And the blue cells are those that you make a lot of false positive. And the black ones are those you miss. You don't make any false positive at all. You never respond to them. Of course, between the green and the red, between the black and the blue, you have those. It's a range, not a binary division. You have those intermediate situations. Based on this, I'm sure if you have been listening carefully, you can easily discover some regularity. First is that in those easier ones, means green ones, atoms are often next to each other, right? And in those more difficult ones, atoms are often scattered. And another observation is that for the empty cells, the blue ones are often those that's next to items, right? For those far away from all items like this, it's almost always black. So what would you see based on those observations? A plausible account is that the location of items encoded with some spatial uncertainty. So basically, when in this example, we have those 2 items, you can remember them fairly good, fairly well, but it's not completely precisely. And sometimes the signal of each item will fall in those neighbors, areas, neighbor cells, and you do respond to those. And the response is determined by the sum of all distribution of 8 items. And the responses are decided by the portion in the sum distribution. So basically, if an item has neighbors, they may be confused with each other and might still be correctly reported. And also, so that's why when they're next to each other, you are more precise, and also like you get responses in those neighboring items. So this explains both of these observations pretty well. And this is what I call a baseline model. It's pretty good. This is the prediction of the baseline model. If we compare that against the actual data, you can see it's fairly consistent, but not completely the same. And then we try to figure out the other mechanisms as well. So that's the development of a comprehensive exploration model. Basically, approximately 24 mechanisms were tried, but either because they were conceptually relevant or because they were identified in a comparison with the CNN neural network. So that's I will explain that, get to that later. But for now, just remember that those 24 mechanisms were either included for conceptual reason or empirical reason. And about half of them, 12 of those mechanisms were kept in the model because they significantly improved the model. So what are those mechanisms? I will explain a few of them, those more important ones. The first is the Bayesian integration. So what is Bayesian integration? I'm sure all of you know that the concept and the mathematical principles. I wouldn't bother to explain that. So those are the basic formula being used here. But conceptually, this is the way how it matters. So basically, if you have an item that has a label, and because that for that reason, some signals spill over here, and they'll make this give this higher signal, and so make it more precise. Make it more precise, then the Bayesian priors have a less effect on this because this is more precise, but have a more effect on larger effect on this because it's less precise. So this is the way how Bayesian integration works in this particular study. And we found that the Bayesian priors have this are distributed like this, and also the representations are distributed like this. I modeled those, but the conceptual reason is not entirely clear. And another important mechanism is what I call out-of-range signals. To put it simply, observers. So earlier I said that the signal sometimes will go to the label cell. What if an item is already on the border? If it's already on the border, then you don't get another label item. So what will this part do? So theoretically, I assume that this part will be recycled back to this location, at least partly. So intuitively, this means like when observers remember the items, occasionally they will remember an item is outside this 6x6 array, but they also knew that is impossible. So they figure, okay, my memory must be wrong, but I still want to make use of my memory. So I will just report the one that is the closest to that memory. So that's how this works. And we have the effect of grouping. So grouping in this particular case works like this. In a grouping mechanism, 2 or more consecutive items are treated as a whole group, and their lateral positions are remembered more precisely at the cost of their radial positions. In addition, neighbors repulse each other. And we also have this additional components. What are the additional components? So if you have heard about the multiple spatial frequency analysis, then that's similar to that. So basically, in addition to the primary components, We also have a high precision components, which is like a very precise. We also have low precision components, which is very blurry. Those also contribute. This is the main mechanism, but those also contribute a little bit to the final outcome. So those are what I call additional components. So in addition to that, we also have categorical memory. What is categorical memory? There are two particular mechanisms like in this category. The first is line detection. The second is gap detection. Line detection, you try when you see a few items connected like a line, you remember that like purposely, like just a specialized mechanism as a line. And then when you see a gap, you remember that as a gap, something like that. And we also have the what I call whole pattern indexes. Whole pattern indexes are three subcomponents. So the first is that the average of all signals also matters. Means that if an item has a few high signal like items, then that will further help all items. And also, if a pattern includes some clear-cut trunk like this, then that will help all items again. And again, if a pattern includes some some items that's repeated like this, that will help all items. So what is interesting in all these cases is that it will help all items. For example, here, you know, when this repeat with this, they will be improved. That's obvious. But the interesting thing is that they will also help those to the same extent. And the reason is not entirely clear. And I suppose that's because observers can flexibly trade off between the items. If an observer's memory is enhanced with a specific item, then resources will be moved away from that item. So the benefit will be equally shared by items. So combining all those together and adding a few other less important mechanisms, I have this full comprehensive exploration model. And so this is the structure of this model. Okay, so like in the rest of the talk, I want to discuss implications and a bit of the future directions of this large scale experiments. So first is that people always ask, why this model? What's the advantage of it? First is that it's a good overall picture. It's a tentative overall picture. So what does it mean? For that, so I compared against two benchmarks. Like a lower limit in the baseline model, as we discussed earlier. That's more typical, more like a typical psychology model, psychology theory. Very simple, can explain the data reasonably well, but not complete. It's not the complete story. And on the other hand, we have I built a CNN neural network to try to capture all the mechanisms in this task. And as expected, the CNN neural network is always the best. And this comprehensive exploration model I proposed here is a bit worse than that, but it's much better than the baseline model. The point here is that the comprehensive exploration model is much better than the baseline model and nearly as good as the CNN network. So not as good as, but nearly, but it's much simpler. All in all, the comprehensive exploration provides a tentative overall picture. It's an efficient summary of the underlying mechanisms of spatial working memory. In the last 10 years, a new type of neural network, like deep learning, has changed our world. So I want to say a few words about neural networks. It's probably not necessary for this audience, but I included this for the psychology students. So I'm sure you all have heard AlphaGo, AlphaFold, and ChatGPT, which I actually used to prepare this PowerPoint. So all of those are very impressive, but it's not that they have no problem. However, neural networks are not interpretable. So those are of course not interpretable, but even the relatively very simple neural network I have built in this study is not interpretable. So these are the features extracted by those neurons in the last layers in that like network, and you can see it's not clear. There's no conceptual interpretation, no clear conceptual interpretation of what it is doing. So together, now in this particular case and in many other areas of psychology and just in this whole world, we have traditional psychology theory that's highly interpretable but not effective. We have neural network that's highly effective but not interpretable. So my example is just a small example, but there are many real-world examples. For example, we all know that face recognition. We have those psychology theories that based on parts and the feature and also configure processing. It's highly interpretable, conceptually very clear, but it has a problem because simply couldn't explain the data very well. On the other hand, we have like the neural network, deep learning, face recognition, neural networks that's being used everywhere, and however, it's not interpretable. So in this situation, this kind of comprehensive exploration model, as I try to propose here, has its use, which is a good combination of those two. Okay, I also want to compare the comprehensive exploration model over the typical one mechanism studies. We have some advantage. The advantage is that they give fragmented pieces of findings, and we give a tentative overall picture. For most people working on this, many of them, they have this reaction that, wait a minute, we don't just have fragmented pieces. We do have that perhaps in individual papers, but we have literature review, which can tell you the overall picture. So how is your comprehensive exploration better than literature review? So I argue that it's better than literature review for at least two reasons. First is that if something is missing, we can immediately know it from the lack of a good fit. But in the literature review, if something is missing, that is not necessarily obvious. So for anyone who has several years of research experience, I'm sure you know that when you read a literature review, you see it depends so much on what happens to be popular at this moment and what happens to be picked up by some well-known researchers, and that's leading researchers. And but there are some other mechanisms which could be equally important or maybe even more important, but people may easily ignore them for 10 years, 20 years without studying them at all, like simply because no one picked it up. And on the other hand, so that's one advantage of comprehensive exploration. We always it's always obvious on the reader, like if something is missing. And on the other hand, when two mechanisms or multiple mechanisms overlap with each other, it's also obvious in the comprehensive exploration because that filters out redundant mechanisms automatically. On the other hand, it's not always true in literature review. And I'm sure it's the case in many areas, if not all areas. For example, in working memory or processing of spatial information, we have segmentation, we have clustering, chunking, grouping. Many years ago, I wondered, are they totally separate mechanisms? Seems not. But people just study them in slightly different way without, maybe they occasionally discuss that in a general discussion, but nobody knows whether they are the same or they are different. How so? So it's just a mess. But once we have the comprehensive exploration, it's clear that chunking and grouping still matters after other mechanisms considered. But segmentation and clustering have tried both and have rejected both because they do not improve the model. Supposedly because they have already been covered by other existing mechanisms. Okay, so after trying to defend this approach, of course, I want to say that my approach is good, but I also want to make it clear that it's not all good. It also has this problem. So first is that the comprehensive exploration has the unique advantage of showing the tentative overall picture. However, this overall picture is tentative as an initial attempt at creating an overarching framework. The model probably can and indeed should be further improved in future studies. If any of you, I'm sure there are a lot of very good modelers, much better than me, in the audience. If you're interested, please download the data and the model from the paper that's open access online, and feel free to try it, and it would be great if anyone can improve it. I'm pretty sure that this current model is not optimal yet, should be further improved. And also, if you're interested in conducting a large-scale experiment on your favorite topic, please do not hesitate to contact me. I would be happy to discuss the possibility of collaboration with you. Over the years, our lab has developed our own data collection platform, which is not very flexible. It can only be done to do large-scale experiments. It's not flexible, but it's more efficient than MTurk. When I say more efficient, it means more cost efficient. As a result, we were able to successfully complete data collection for 3 following large-scale experiments using our own platform, after this study I have just discussed. So, and right now the speed is about 2 experiments per year. We can do that, and we have some free capacity because I couldn't analyze the data at a so fast. So we welcome collaborators. So there's acknowledgement for the GRF grant, and this is my contact information. And please contact me if you're interested in this topic. Thank you. So now the Q&A session.
Yeah. Okay. Thank you very much, Professor Huang, for very stimulating talk. So I guess that many of us, in particular from the computational social science, that have already have a lot of questions for you. So Professor Tan, do you want to go first?
Oh yeah, Professor Huang, I'm so happy that you spent the time talking to us. It's a CSS group. From the perspective of CSS, I have 1 comment and then 2 questions. I'm sure others will have raised other questions in my mind as well. My first comment is really congratulations to you for telling us, sharing with us, lovely intellectual discovery story, how you work from one paradigm of design experiment, discovering truth, to another kind of paradigm that is all the more exciting and falling in line with both Duncan Watt's advice and the CSS movement that the audience here are all championing wholeheartedly. So my two questions are: first one, I've kind of highlighted in the chat room, saying that you refer to the trade-off between effectiveness and interpretability. More often within the CSS community, we think about model fitting, goodness of it, what you call kind of effectiveness versus potential of overfitting. Fitting well it cuts both ways. It looks fitting data better, seems to be closer to the truth, but actually it could be further from the truth, leading us astray. In your case, how do you, when you evaluate effectiveness and interpretability, the latter being quite subjective, seemingly cannot quantify, how do you at the same time take into account potential for overfitting? In your subjective statement earlier on, you said you got too much data. It's a headache. It's witness curse, kind of. So how do you do the trade-off as a practitioner?
Okay. So if I understand your question correctly, it's like the criteria of model selection, right? Model comparison, and like others, I use AIC and BIC and those indexes. But the difference is that because as far as I understand, people don't use those always in exactly the same way. Some people may say AIC, if there's a difference of 10 or 20, that is good enough to accept a new parameter or new mechanism, etc. But I use a much more strict rule than that. I use AIC difference of 5,000 before I accept the mechanism. So in this sense, one will probably see that this model is underfit, it has underfitted a lot. But because although I switched to large scale experiments, I am still a experimental psychologist. I still care mainly about interpretation. So I prefer to underfit than overfit. So I only stick to those that with the most clearest interpretation, with the most obvious, most strongest effect. So, but I'm not saying that, I'm not trying to argue that my standard is the best or even better than any other study. So it's all for different reasons. And for my purpose, I choose a very strict AIC standard. And that's just one standard. I'll also use divide the data into 10 subsets and see whether they generalize very well. I also use those kind of standards. So, but overall, I prefer to stay on the conservative side, to just try to prefer to underfit than overfit. So, yeah. Your second question?
Thank you. I think you get my point, and I appreciate that. My second question is related to research design.
Yeah.
My the main takeaway from your talk, which is already suggested in the way you formulate the title, you're advocating for a large-scale experiment. This is changing from a lab-based experiment based on a few experimental designs, then publish a paper. You have literally thousands of experiments all at once and pull all the information across so many experiments to draw what you call a single coherent piece of empirical basis to make a decision, a theoretical conjecture. What makes this possible seems to be going online, collecting data online. Is that really the technological breakthrough you are riding on to enable this? Nobody would disappear that the more the better, right? The more we experiment putting together, the better. would you say that it's all because the ability to go outside the lab, go to the field, not really go to the field, go online to collect big data? Is that right? Is that the key that you are able to undertake to make use of this new experimental design strategy?
Yes, that's the basis of our large-scale experiment. Otherwise, because I wanted to do this actually some years ago, like it's not just a theoretical reason or I didn't realize this. I wanted to do this 10 years ago, 15 years ago. But back then I realized it would take me a few GRF grants to do one experiment, which like is obviously impossible. But now with the online data collection and basically I set up this I presented this as a small game on cell phone, a mobile phone. And then the way I do it, it's like endorsed by the social science, ethical approval. So basically, I set up a competition. I don't pay all of them. I set up a competition, and they have to be better than a certain ranking, so they can get paid. And because they compete with each other more and more, and I get more and more data. So that's how I can get more data with less cost. I would say like it's probably it's only 20% of the cost in the lab. If you count the cost of a research assistant, it's maybe even just 10% of the cost in the lab. So
wonderful. Congratulations.
Thank you. So it's like before would take like 3 GRF grants to do one experiment. And now we can do 3 experiments with 1 GRF grant. I mean, still fairly large, but at least it's possible. Like before, it's entirely impossible. Yes.
Yeah, wonderful. Thank you.
Okay, Professor Jamie Ni from sociology also has some questions.
Hi,
Jamie. Yeah.
Hi, nice to meet you. I'm a member of computational science lab and assistant professor in sociology. So basically, I think I have a similar spirit from Professor Tam's question, but totally admit like I'm so dumb about the psychology and memory matters. So feel free to educate me on this question. So I was a bit more wondering about your results. So how did you quantify the order of the importance of this large set of mechanisms? Was it like something that you proceed to falsify like null hypothesis for each mechanism? And I was also wondering like what were really true and what were less true to explain the pattern. Because in sociology, like we kind of focus on one mechanism and maybe do research to falsify the others and things like that. And I also think that it sounds like these mechanisms can be like mutually exclusive, because I think maybe some of the mechanisms like overlap each other. I don't know what like memory matters, but kind of think that maybe some different mechanisms can fall into a sequence in a big picture, right? And things like that. So my question is about like generally like the presentation of the results and how did you order like what is kind of more important, what is like less important and things like that. How
so it's like so if I understand your question correctly, it seems that you're asking if there are any formal and procedure of selecting and producing this mechanism. Unfortunately, I don't. And although I'm trying to think about it, but it seems difficult. So to compare it against some other model, like for example, multiple regression or structural equation model, or even like a neural network. So those well-established type of model, they always have a formal procedure, a standard procedure of like, for example, in multiple regression, you have components. You can compare the contribution of each of them, and but in the model I'm trying to build, it's a highly nonlinear model, and it's not linear at all. And I actually tried. If I do it in a linear way, then it would be much worse than it is now. So I think like first, it depends a lot on familiarity with literature. So this is not something that anyone can do in any area. You have to work on an area that you're already familiar with. So you already kind of know those are the factors, mechanisms, and you have some rough idea about how they should work together. And then you try those plausible way of combining them, and you get an answer. And again, I want to say that I don't think I already get the optimal way of building the model, and I think it can be and should be improved in the future if someone takes the effort to do it. So this is the best I can produce, but I'm sure there are better ways of doing it. So I hope this answer wouldn't disappoint you, but mathematically there's no, it's not like multiple regression. You have like a standard way of doing it. There's no standard way of doing it. It all depends on your familiarity with the topic. So yeah.
Thank you.
Okay, any other questions? We still have time. We can take a one or two even more questions.
Yeah, let me return to Jimin's question. Even though Professor Huang has initial answer, I'm thinking of the following situation. In statistics, in experimental statistics, there's a theory for pretty advanced theory, mathematical theory for how to optimally design factorial design of an experiment, so that just like in sample size, too much is inefficient. Too few is also statistically inefficient. There is a theory for optimal sample size for reaching certain statistical power. I'm wondering, when you go so big, go to big data approach to designing tens of thousands of stimulus to get good data, wouldn't you sooner or later have to come up with some, not rules of thumb, but systematic way to justify at least have how many stimulus, or how diversity of stimulus and so on, instead of saying that depending on different questions, different research topics, we may need different set of stimulus design. That seems to be you have to be highly experienced before you know how to do it well. Then for a student, and as beginning student trying to do his or her dissertation, it may be really challenging, right? So it is, I'm wondering, after working through several projects so far, can you say something a little bit more for even someone like me in computational science? I want to generalize some take-home lessons from this.
It's difficult because I'm now discussing like this with several collaborators, and it's actually a challenge for us to determine how broad or how comprehensive it should be, because like if we include too many aspects, you may easily find that even a large scale experiment is insufficient. But if we don't include like enough aspects, then it will become a waste of the resource. You found that, okay, there are not much details in that data set anyway. So I don't think there is a good way of doing it, but there's a perfect way of doing it. But the way how I do it, one way is to look at the literature and see in those normal size experiments. For example, if they have 3 conditions or 10 conditions, and take maybe, for example, 10 conditions, they take 100 hours of data to have a clear story, clear picture, then we may assume it can be generalized. Like if we want to include maybe 10,000 conditions, then we want to have like 100,000 hours. And I normally also try to recommend to like to have some to leave some room as a like a buffer to double that, and then I use that to determine the number of conditions that should be included. But it can always be surprising for reasons that's not clear. I will give you one example. For example, in one study, one follow-up study, I tried to look at aesthetic preference among those 80,000 patterns I have used in this study. And I looked, because I don't know much about beauty and aesthetics, that area, I looked into some of those papers and get some sense. And I realized that it's normally quite demanding. And for that reason, I because I thought about expanding it, but so okay, I probably shouldn't. But then, surprisingly, when I got the data is much more consistent than I have predicted. So much less noisy than I have predicted, because I thought people would disagree with each other a lot on which one is more beautiful, but actually they don't. And so that would be a case that so I have underplanned, but it doesn't really matter for now, because now it's experiment is conducted in the session of weeks. I just spend less money on that. But in the future, if we do it more efficiently, try to do everything with a very large sample, that's my long-term plan, then that may lead to some waste of the resource. But there's not much we can do about that, because we do planning, but the planning can go wrong for reasons that's not clear for now. Yeah.
Thank you. Thank you.
Okay, any other question from the audience? So if no, I have a question. Okay, probably the last question. So as I just mentioned, it's quite stimulating for computational social scientists. So very appreciative your very rich experience. Actually, you explained how users need you to this kind of large scale experiments. So you just mentioned, so think about that. If there is no a unified theory can explain everything in the real world. So if you use a purely data-driven approach, and you can easily detect some patterns, like using the deep learning or whatever. So this is quite similar to a claim in the early stage of computational social science that is the end of theory. So the thing is that given that there is no unified theory, and there are new tools that can detect any patterns that if you have enough data. So why we need a theory? So just one. This is a very broad question. I know. Just want to know what do you think?
Well, I don't. Well, that's too philosophical.
Yeah.
But I can just give you what I think. I don't know if it's even good at all. But I think the reason, the very reason why we need interpretability is that because when something is conceptually clear and interpretable, it is more likely to be generalized to another situation that's conceptually relevant, but empirically very different. For example, like aesthetics, what is beautiful? If we have some understanding about what is beautiful in like a painting, then a good conceptual interpretation, then we may be able to generalize that to like facial attractiveness, or just photography, or even just clothes, or whatever that is on the conceptual level. But it seems difficult if we try to generalize a neural network that was built for one type of beauty task to another totally different type of for example from the photography to facial attractiveness. So that's why I think one reason why conceptual interpretation is useful. Another reason is because for pure theoretical reason, because we are, when I say we, like one is like all human, but also particularly the scientists, like researchers, curious about how the world works. Like, so even if it doesn't have any practical value implication, it is still useful because it can satisfy our curiosity. But actually, I had a discussion with a friend some days ago regarding a question that's similar to yours. Like, he is an engineer in Google and working on the artificial intelligence there. I don't know exactly what his role in those new developments, but he's pretty senior, so he should know enough about it. And he always laughed over the years at us, saying we're trying to figure out the way how those things work is a waste of time. And then, like several days ago, I asked him, so do you actually just think we should give up on understanding the way how mind works, just relying on neural network, and eventually we don't know how it works, but we build networks that works? And he said, actually, no. He said, we will eventually know, but not by figuring out ourselves. The way how he designed it, or maybe how they design it, is that he thinks they will try harder and harder to build more powerful, like neural network. And I think the GPT is kind of like already going in that direction. Maybe not exactly there, but maybe in 20 years, like can be like that. And then once it reaches a cutoff point, a threshold, that the neural network can design another neural network that's even better, so it can come into the stage of self-reinforcement, and eventually it will automatically build better and better neural network that can study itself and can study human mind, can figure out how to work conceptually and then tell us. So that's what he thinks the way of doing it is to produce powerful AI, and the AI will study itself and figure out the conceptual reason why an AI or human mind, whatever, works like as a mind, and tell us the conceptual reason. So I don't know, it's more like a scientific fiction, but he seems to be serious on that.
Okay, thank you very much. Any additional questions? So if not, let's thank you, Professor Huang, again for very interesting and stimulating talk.
Bye.
Thank you.
Okay, thank you. So bye.
Welcome again.
Yeah.
Bye.